Hello everyone, and welcome to our discussions on differential amplifiers. So in the previous lecture, we have been looking into the single-ended and differential operations. We have already discussed what does a single-ended signal mean. It's basically you are considering the signal between the terminal of interest and the ground. On the other hand, differential signaling means that you're considering the difference of signals between two terminals and none of them are ground. Also, at the same time, uh, the differential signals are defined as 180-degree opposite signals of each other. So they will have phases which are 180-degree opposite of each other. So if one of the signals look like this, that a positive half of the sine wave is considered first and the negative half of the sine wave is considered second, for the other input, the negative half of the sine wave has to be considered first and the positive half has to be considered next. We have also looked into the advantages of differential operation, that if there is a capacitive coupling between, let's say, a clock line or any other interference line or aggressor line with the output, we have seen that if we are using differential signaling, then the effect of the aggressor goes away. And that is same for interference as well as noise. For example, in this slide, we had seen the effect of supply noise, which for a single-ended operation will be available at the output. But for a differential operation, as both of the outputs are getting subjected to the same amount of noise, the difference of those two outputs will be a clean sine wave. Similarly, we have seen more examples of victims and aggressor. For example, in this case, even if we had a single-ended analog line, but there are two digital lines going in parallel with that particular analog signal line. And these digital lines, if they are differential, let's say they're clock and clock bar, in that case, they will affect the signal line in a similar way. And again, you'll see very low amount of interference or very low amount of signal coming from the aggressor to the victim line. All right. And we have also looked into the different ways to create a basic differential pair. And the simplest way to create the basic differential pair is to have two of your common source amplifier. So for example, here on the left-hand side, we have put one common source amplifier, and on the right-hand side, you have put another common source amplifier. You're providing input voltage 1 to the first common source amplifier and input voltage 2 to the second common source amplifier. Now, if Vin1 and Vin2 are differential versions of each other, which really means that you have a sine wave looking like this at Vin1 and a sine wave looking like that at Vin2. In that case, Vout1 minus Vout2 will be an amplified version of the difference of these two input sine waves. So that's why this is called differential amplifier. It takes differential inputs and you can have differential outputs. But one consideration here is that as you have these differential inputs, Vin1 and Vin2, you already know that for any kind of amplifier, you have to first set a DC biasing point, and then you can apply an AC signal so that the amplifier can amplify the AC. Now, of course, from your understanding of the VTC curve, you know that your input DC bias point needs to be somewhere close to the difference of the VDD and VSS lines divided by 2. So in this case, it's VDD minus 0, which is your VSS or the ground line, divided by 2 will be VDD over 2. So your input and output DC biasing point needs to be close to VDD over 2. If it is not the case, for example, let's say you reduce your V in CM, that is the common mode or the biasing DC biasing point at your input. If you reduce this DC biasing point, what will happen is that this DC value will go down. So for example, here, let's say this axis represents the ground. And in this case, you probably had, for example, if your VDD is 3 volts, you probably had, let's say, 1.5 volts as a difference between your ground line and the DC common mode line. Now let's say you have reduced that 1.5 volt to only 500 millivolt. In that case, what will happen is that in your V in versus V out characteristic, that is your VTC, now you are far on the left-hand side because your V out is smaller or your V in is smaller in this case. So you have reduced your V in, the common mode value of your input voltage. So you have moved towards left on the VTC. If you're moving towards left, your V out keeps on increasing. So what is happening in this case is that as you reduce your V in, the DC value of your V in, the DC value of your V out will increase. So in the previous scenario, the V out was also, let's say, very close to VDD over 2, but now it increases and goes closer towards VDD. Now, the problem that you might see in this case is that as you have a sine wave, so your V out CM is definitely less than VDD, but since you have a sine wave, the top of that sine wave can be clipped off. So there is a possibility if your V out CM goes closer and closer towards VDD, that the top of your sine wave will be clipped off. So now what you see here is that as your input common mode changes, the output common mode also change. And that comes directly from the VTC characteristic that we had learned before. Now, there is one way to avoid this particular condition. That is, if you connect the sources of the two input transistors. So in the previous case, these were your input transistors, right? M1 and M2. And RDs were your load resistances. Now, what you're doing here in the next slide is that you're connecting the source terminals of M1 and M2 together, and then connecting a ISS current source at that particular terminal. And of course, you're assuming that both M1 and M2 are very identical. Also, RD1 and RD2, these two resistances are identical. Now, this differential pair will incorporate the current source ISS to make the total current flowing through the entire component independent of the input voltage. And why is that? That's because let's just first assume that your input voltage 1 is equal to input voltage 2 in terms of DC. Then the bias current of both M1 and M2 will be equal to ISS over 2. Again, why is that? That's because your M1 and M2 are both identical. Your RD1 and RD2 are identical. If your input voltages are identical, then the left-hand side of this particular component and the right-hand side of this particular component are symmetric to each other. So this part is symmetric to the other part of the circuit. So these are called half circuits, and we'll discuss more about half circuits later on. So this is just half of the full component. Now, if both the halves are exactly identical, then the total amount of current that can flow through the left-hand side has to be equal to the total amount of current that is flowing through the right-hand side. And that current will be equal to ISS over 2, because the total current that can flow in this case is equal to ISS. And that's just because of KCL, because you already know from Kirchhoff's current law that if there are two currents flowing in these two branches, they will get added and then they will flow through this combined branch. So if the current in the combined branch is equal to ISS, the individual currents in the two branches has to be equal to ISS over 2. Now, if these two currents are equal to ISS over 2, then the voltage drop across RD1 will be ISS over 2 times RD1. The voltage drop across RD2 will be ISS over 2 times RD2. So the voltage drops across RD1 and RD2 will also be identical. And as the voltage drops across RD1 and RD2 are identical, the voltages at point X and point Y will also be identical, because the voltage at point X will be VDD minus RD1 times ISS over 2, and the voltage at point Y will be equal to VDD times VDD minus RD2 times ISS over 2. So these two voltages at point X and point Y will also be equal, because the voltage drop across RD1 will be equal to the voltage drop across RD2. Now, if the common mode voltage of your input changes, so let's say your Vin1 and Vin2, at these 2 points, your common mode change. Even in that case, the total amount of current flowing through the entire component will be equal to ISS. Because as you are changing the gate voltage at Vin1 or Vin2, what will happen is that this gate to source voltage, so the current through the device is a function of the gate to source voltage, right? It's not only a function of the gate voltage. You know that the current through an NMOS device is equal to K over 2 times VGS minus VT whole squared. Now, because you have VGS in that equation and not only VG, as you are increasing the VG or V in of this device, if the source voltage also increases, so let's say you're increasing your VG, at the same time, if your source also increases by the same amount, your VGS will stay same. And if your VGS stays same, then the current through the device will stay same. So that is the way. That is basically a negative feedback that you inherently incorporate in this entire structure, because of which the current through the individual devices remain constant, even though the voltages at VIN1 and VIN2 are moving up and down. So in this way, the total current as well as the individual currents become independent of the VIN-CM, assuming that, of course, the VIN-CM is equal for VIN1 and VIN2, that you have a common mode for VIN1 and VIN2, and that common mode is same. It's same for both the inputs, but it can vary over time. So for example, let's say initially the common mode could have been 1.5 volt, and then with time it could come down to 500 millivolt. But assuming that all the transistors are still in saturation, the output voltage will not change in the second scenario in the next slide, because the current in the individual branches are not changing. So another way to understand this is that let's just consider the case when your input voltage 1, VIN1 is much more negative than VIN2. Let's just consider that the DC voltage at VIN1 and the DC voltage at VIN2 are not equal to begin with. So when VIN1 is much more negative than VIN2, that is the DC voltage at VIN1 is much lower than the DC voltage at VIN2, it could be, it is very much possible that your M1 transistor is off, and it will be off if the VGS, the gate to source voltage of the M1 transistor, is less than the threshold voltage of the M1 transistor. And in that case, the entire current that flows through this tail transistor, so eventually this current source will also be implemented using transistors, and you already know how to implement current sources and current meters using NMOS or PMOS transistors, right? So we have seen that in one of our previous lectures. So right now, let's just assume that this is a current source. Eventually, it will be implemented using a transistor. This is called a tail transistor because this looks like a tail of this entire structure. So if you just probably assume that this structure to be some kind of an animal, let's say a mouse or a cat, this looks like the tail of the animal, right? So that's the reason why this is called a tail transistor. Now, this tail transistor's current, or through the tail current source, the amount of current that you have is equal to ISS. If M1 is off, then the entire current ISS will flow through this M2 device. So, and you can readily understand why it will flow through the M2 device, because M2 is on as the value, the gate voltage, the DC voltage value at the gate of the M2 transistor is much larger than the gate voltage at the input of the M1 transistor. So M1 is off, M2 is on, and the entire current flows through this M2 device. In that case, ID2 is equal to ISS. The current through the second branch is equal to ISS. Vout1 will be equal to VDD. The output voltage, DC output voltage at the X terminal, terminal X, will be equal to VDD. Again, why is that? Because you know that the voltage at this terminal is equal to VDD. There is no current flow in this branch, which means that there is no voltage drop across RD1 in this branch. So whatever voltage was present in the top terminal of RD1 will be the voltage at the bottom terminal of the RD1. So Vout1 will be equal to VDD. Vout2, on the other hand, will be equal to VDD minus the current flowing through this branch times the RD2 resistance. So Vout2 will be VDD minus RD times ISS. Now let's just assume that your DC input voltage at the gate of transistor M1, that is VIN1, is brought closer to VIN2. In that case, M1 will gradually turn on, because gradually you'll see that the VGS across M1 will keep on increasing, and it will start drawing a fraction of the total ISS current. And as it draws a fraction of the total ISS current, ID2 will start falling. As ID1 starts rising, the current through the M1 transistor starts increasing, the current through the M2 transistor will start decreasing. That's because, again, ID1 plus ID2 has to be equal to ISS because of KCL. When you have Vin equal to Vin2, Vin1 is equal to Vin2, when you have both the input DC voltages to be equal, in that case, your output DC voltages will be equal to VDD minus RD times ISS over 2, because both branches will carry a current of ISS over 2. So both the drain resistances will have a voltage drop of RD times ISS over 2. And that's why the DC voltages at Vout1 and the DC voltage at Vout2 will both be equal to VDD minus RD times ISS over 2. That's the output common mode level. Now, on the other hand, when Vin1 will become more positive than Vin2, ID2 will start becoming larger than, ID1 will start becoming larger than ID2. So the current in this branch will start becoming larger than the current in the second branch. And as a result, Vout1, the voltage at point X, will drop below the voltage at point Y, which will be equal to Vout2. And again, when you have a sufficiently large Vin1 minus Vin2, M1 will start drawing all the current, because M2 will become off and M1 will be on, as Vin1 is much, much larger than Vin2. But always you have to keep all the transistors in saturation. We'll come to that. But assuming that all the transistors are in saturation, in that case, when Vin1 is much larger than Vin2, M1 will start hogging all the current ISS, and M2 will turn off. In that case, Vout1 will be equal to VDD minus RD ISS, and Vout2 will be equal to VDD. Graphically, if we represent this, then the plot will look something like this. That, let's say, in the x-axis, you are representing Vin1 minus Vin2, and the y-axis, you are representing the output voltages. So either Vout1, which looks like that, or you're representing Vout2, which looks like this. So as your Vin1 and minus Vin2, Vin1 minus Vin2 is a large positive quantity, which means that Vin1 is much, much larger than Vin2. In that case, your transistor M1 will hog all the current. So if we go back to the previous slide, as your Vin1 is much larger than Vin2, this transistor M1 will be on and M2 will be off. So all the current will flow through this branch. So Vout1 will be equal to VDD minus ISS times RD1. That's what you see in the next slide, that Vout1, which is this curve, will be equal to VDD minus ISS times RD over 2. Or the over 2 component will not be there. So it will be VDD minus ISS times RD. So that's what you see in this side. But that's the value of your Vout1, when your Vin1 minus Vin2 is a large positive quantity. Similarly, when Vin1 minus Vin2 is a large negative quantity, then the value of Vout2 will be VDD minus RD times ISS. On the other hand, Vout1 will be equal to VDD. So that's just a graphical representation of what we had discussed in the previous slide. But of course, if your Vin1 minus Vin2 is equal to 0, that is, you are exactly applying the same voltage at both the inputs. In that case, your output voltage, Vout, will also be same. And that will be equal to VDD minus RD ISS over 2. So both the output voltages will be exactly equal. So the difference of the output voltages will be equal to 0 if the difference of the input voltages are equal to 0 for an ideal differential amplifier. We know that in real world, the differential amplifiers are not ideal. And in that case, you might have something called an offset voltage. And you are seeing that as part of your lab 6 experiments, that even if you apply the same Vin1 and Vin2 in terms of DC, the DC values at Vout1 and Vout2 may not be exactly the same. That is because in the previous slide, one of the biggest assumptions that we had made is that the left-hand side is exactly identical to the right-hand side. That will not be the case in a real scenario, because the RD1 may not be exactly equal to RD2. The properties of the M1 transistor may not be exactly equal to properties of the M2 transistors, and so on. And because of that, even you are applying the same DC voltage at Vin1 and Vin2, your DC voltages at Vout1 and Vout2 will not be equal. To make Vout1 and Vout2 equal, you have to change one of the input voltages, keeping the other one same. So you might see that Vin1 minus Vin2 could be equal to maybe 10 millivolt or 15 millivolt to make Vout1 equal to Vout2 in a DC sense. All right. So we have already understood the effect of changing your VIN1 and VIN2 DC voltages and how the DC at the output will change according to that. So this is how the graphical representation looks like. And if you represent Vout1 minus Vout2 on the y-axis and VIN1 minus VIN2 on the x-axis, then you'll see that this curve uh, will have values from plus RD times ISS to minus RD times ISS, depending on whether VIN1 is larger than VIN2 or VIN2 is larger than VIN1. Now, of course, as you see that for larger differences between VIN1 and VIN2, the difference between Vout1 and Vout2 becomes almost constant. On the other hand, if the difference between VIN1 and VIN2 is 0 near to this point, the difference between Vout1 minus Vout2, that's also 0, but the slope is maximum, right? Near to this point when VIN1 minus VIN2 is 0. So near to the point when you have the DC voltages of the inputs are equal, near to that point, you'll have the maximum slope, which also means that you'll have the maximum gain. So as your VIN1 minus VIN2 becomes large, either a large positive quantity or a large negative quantity, your gain becomes 0 because the slope of this curve becomes 0. On the other hand, near to this point, the slope of this curve is maximum. And of course, another way to represent that or another way to explain that is that the circuit will become more and more nonlinear as the input voltage swing increases. So as the input voltage difference in the input voltages increases, you already know that the MOSFET is a nonlinear device. And why do we call the MOSFET a nonlinear device? Because you know that the MOSFET, to the first order, it satisfies the square law equations. And what is meant by square law equation? That's just that the current through the MOSFET is equal to K over 2 times V overdrive squared. So as you're changing the input voltage, the current changes as a square quantity to the first order. Of course, there are other non-idealities or second order effects because of which it will not follow the square law model exactly, but you can approximate the behavior of the transistor with the square law model that you have used in your homeworks or in your exams. Now, of course, if it is squared, then it is nonlinear because you know a linear expression is something such as y equal to mx or output equal to a times input. But because the transistor's current follows a square law model with respect to its input voltage, it is nonlinear. But in a very small range, you can approximate it to be linear. And this is the nonlinearity, that's what you are seeing, that in a large range of input voltage change, the output voltage change in the output voltage becomes nonlinear. But in a small range where VIN1 minus VIN2 is almost equal to 0, you can approximate the change in the output to be a linear function of the change in the input. So that's why for any kind of amplifier, linearity is a big deal. Linearity is a big concern because as your input voltage becomes larger and larger, your output or the gain of the system will not remain a linear or will not remain constant. So your gain keeps on changing as your input voltage swing keeps on changing. But in a very small range, when your input voltage change is small, you can assume that the slope of this curve is constant, which means the gain is constant. And that's why we talk about small signal models, that your input needs to be small for your gain to be constant. If your input is large, your gain will not be constant, and any of your small signal analysis or your AC analysis will not remain exactly true. And that's the reason why we call it the small signal analysis. One other thing is that when VIN1 is equal to VIN2, the overall circuit is said to be in equilibrium. So this is the equilibrium for this particular differential amplifier. Okay. So the effect of this tail current source is that it will suppress the effect of any kind of common mode variation on the input. So if there is a common mode variation at the input, you'll not see that variation at the output level. So that's the job of the tail current source. And you can implement the tail current source with a transistor, a current source bias transistor, something like that. And this can be a current mirror, as you can connect maybe somewhat like a circuit that you have learned before, that if there is a current source like that, and if there is another transistor on the left hand side, so make that diode connected and connect the gate of these two transistors together. So that forms a current mirrored circuit, right? So this is something again you have learned before. You can connect this current mirrored circuit to the gate of this M3, and then M3 will work as a mirror of this original current source that you see on the left hand side. So the current through M3 will mirror the current through this current source, or will be a multiple of the value of the current through that current source. Now, if you set your Vin1 to be equal to Vin2, equal to the common mode value of Vin, and now you vary your Vin from 0 to VDD. Due to symmetry, your Vout1 will be equal to Vout2. Again, we are assuming that the transistors are fully matched and the resistors are fully matched, which will not be a scenario in a real experiment, but let's just assume that for simplicity. Now, when your Vin Cm is equal to 0, both M1 and M2 are off. So M1 and M2, these two transistors are off because your gate voltage at the input is equal to 0, which is equal to the ground potential. So which means that the VGS, if the VGS of the M1 or M2 transistors needs to be more than VT, then the voltage at point P has to be negative. Now that cannot happen because you have a positive voltage over here and you have a 0 voltage over here. So in between, at any point, you will either have you can have a voltage between VDD and 0, but you cannot have a negative voltage. If you cannot have a negative voltage at the source terminal, the VGS will not be positive because the VG itself is equal to 0. And in that case, both M1 and M2 transistors are off, which means that the voltage at this point P will be equal to VDD, or will in fact be equal to 0, because you have the M1 and M2 transistors, both are off, but let's just assume that this M3 transistor is on, because you can apply a VGS, which corresponds to a value which is more than the threshold voltage of the M3 transistor, which will mean that this M3 transistor will work as a on switch. If you just assume that the transistor works as a switch, then the voltage at the source terminal will be equal to the voltage at the drain terminal in that case. And which will mean that the VDS will be very small, or in fact will be very close to 0 for that matter. And if the VDS is very small, you know that the transistor will be in triode, because the condition for saturation of a transistor is VDS greater than the V overdrive. So VDS has to be greater than the overdrive voltage for this transistor to be equal to or to be in saturation. But which is not the case if M1 and M2 transistors are off. And if M1 and M2 are off, then the current through this M3 transistor will be equal to 0, and M3 will operate in the deep triode region. And because this I3 or the ISS current in this case is equal to 0, the currents in the two branches, both the branches will be equal to 0, and the circuit will be incapable of any kind of signal amplification. Because you know that for signal amplification, all the transistors need to be in saturation. If the transistors are in triode or in cutoff, which is the case here, that the M3 transistor is in triode and M1 and M2 are in cutoff. So in this case, you'll not see any kind of signal amplification. Your output voltage nodes, Vx and Voi, or Vout1 and Vout2, will both be equal to VDD. And the voltage at this Vp node will be equal to 0. So again, graphically, if we represent this, then we can say that your M1 and M2 transistors, they turn on only if the V in Cm is more than the threshold voltage. So let's say you're plotting V in Cm in your x-axis. So again, V in Cm in your x-axis, V in Cm in your x-axis. And on your y-axis, you're plotting ID1 or ID2 for the left-hand side curve. Vp, that's the voltage at this point. The voltage at the source terminal of M1 and M2, that's Vp. That's something you're plotting in the middle curve. And on the right-hand side, you're plotting Vout1 or Vout2. Now, when M1 and M2 are off, that happens when your V in Cm is less than the threshold voltage. So let's say V in Cm is less than the threshold voltage. So both ID1 and ID2 currents are 0. The Vp voltage is equal to 0. And your output voltages are equal to VDD. But after this point, ID1 and ID2 will continue to increase. And Vp will also keep on increasing as you are increasing the V in Cm. Now, looking back at the previous structure, that as you're applying the V in Cm at the gate of these two transistors, the voltage at point P will follow the input applied as V in Cm, because you know that the M1 and M2 transistors, if your input is at the gate of these two transistors, and if you're considering the source as the output, so you're trying to see that as you're changing the input at your gate, what is happening at your source. So that is basically what a source follower does, right? For a source follower, you have your input at the gate and output at the source. So the voltage at the source of your M1 transistor or M2 transistor, that will follow the voltage at the input, voltage at the gate, provided that the voltage at the gate is more than the threshold voltage. So after this point, the voltage at the source will follow the input voltage linearly. Of course, there would be a gap of, or there would be a drop of the threshold voltage. So your input voltage, if your input common mode is equal to 1 volt, the point Vp will be 1 volt minus VTH. If it is 5 volt, then the value of Vp will be 5 volt minus VTH. So M1 and M2 will act as a source follower, forcing the point Vp to follow V in Cm. Now, when your V in Cm is sufficiently high, then at that point, your Vp, the voltage Vp, which is also equal to the VDS3 of the M3 transistor. So as voltage Vp increases, at some point, VDS3 will exceed the V overdrive of that M3 transistor, and then M3 will also start operating in saturation. And if M3 will start operating in saturation, the current through the devices will saturate. So that's what you see in the left-hand side graph, that the current is saturating after a certain point. And what is that certain point? That's basically your overdrive of the M3 transistor. So if we go back to the previous slide, you need this point's voltage, the Vp voltage, to be at least equal to the overdrive of the M3 transistor for the M3 transistor to be in saturation. So VDS of M3 transistor has to be at least equal to V overdrive of that. And that's the source of your M1 or M2 transistor. So with that voltage, if you add the VGS of the M1 transistor or the VGS of the M2 transistor, then you will reach the voltage of your V in Cm. So V in Cm has to be larger than VGS1 plus the overdrive of the M3 transistor, so that all your transistors are in saturation now. And if all your transistors are in saturation, the current through both the branches will saturate and will be equal. Also, the output voltage will be equal to VDD minus ISS over 2 times RD. And keep in mind that these are all DC voltages. So we are still doing the DC analysis of the circuit. Okay. So now as V in Cm rises further, Vout1 and Vout2 will stay relatively constant. But eventually, M1 and M2 will enter triode region. So as you keep on increasing V in Cm further and further, at some point, what will happen is that V in Cm will become larger than Vout1 plus VTH. Right? So your Vout1 is already fixed at VDD minus ISS over 2 times RD, right? So at some point, as you keep on increasing your V in Cm, that would be higher than your Vout1 plus VTH. Now remember, if I just write this down, that what is V in Cm? V in Cm is Vg at, let's say, the transistor M1. If that is greater than Vout1, which is Vd, the drain voltage of transistor M1, plus VTH. So this we can represent as VGS greater than VDS plus VTH. Or in other words, your VGS minus VT or V overdrive is less than your VDS. So if that happens for transistor M1, then your M1 transistor or M2 transistor will enter your triode region from your saturation. So this is what you will see as your as you keep on increasing your input DC common mode voltage at M1 or M2 transistor, that at some point M1 and M2 will enter saturation. And what is that point? That point will be equal to V in Cm greater than Vout1 plus VTH, as we have just proved from the condition that for the transistor to be in saturation, your VDS needs to be larger than the V overdrive. So this condition comes directly from that equation, that VDS greater than V overdrive means saturation, VDS less than V overdrive means triode. So in this case, Vout1 is VD, V in Cm is VG. So VDS will be less than your V overdrive, and then you'll be in the triode region. Okay, now as you already know your Vout1, you can represent that Vout1 as VDD minus RDISS over 2 plus VTH. So that's your condition, that V in Cm has to be less than VDD minus RDISS over 2 plus VTH. So the total allowable value of V in Cm is within some boundary, that the common mode input voltage, the minimum value of that can be VGS plus VGS1 plus VGS3 minus VTH of 3. That's something we found out from the previous slide, that your V in Cm has to be greater than VGS1 plus VGS3 minus VTH3 for the transistor M3 to be in saturation. The transistor M3 will be in saturation only if this condition is satisfied. On the other hand, the transistors M1 and M2 will be in saturation if the V in Cm is less than VDD minus RDISS over 2 plus VTH. So V in Cm will be in a particular range of voltages. So this is the minimum voltage that you can have, and that's the maximum voltage you can have. Now, of course, VDD plus VTH, that is of larger than VDD. If your ISS is very small, you might see that VDD minus RDISS over 2, that plus VTH, this overall quantity could be more than VDD if your ISS is very small, or if your RD, for that matter, is also very small. So in that case, that's why you have this minimum criteria, that your V in Cm could also be equal to VDD, or it could be less than VDD if this term is less than VDD. Now, beyond this upper bound, the common mode characteristic that is shown here in this figure will not change. So that's why you do not see any other dotted line like this on the larger values of V in Cm, where some of these DC parameters will change. So it's not that these common mode DC characteristics do not change beyond this upper bound, but the differential gain will drop because the transistor will not be in saturation. Now, let's just assume that the input and output bias levels are such that all transistors are always in saturation. And in that case, you'll have a significant amount of voltage gain. So the output swing will be much higher than the input swing. So this could be your output swing, where this is your input swing. Now, for M1 and M2 transistor to be in saturation, each of the outputs can go as high as VDD and as low as V in Cm minus VTH. Why V in Cm minus VTH? Because if the value at the output is lower than V in Cm minus VTH, so that is, let's say at point X or point Y, the value of voltage is less than V in Cm minus VTH. In that case, M1 and M2 will go out of saturation. They will go into triode. And this is something, again, we have proved in the previous slide, that it goes to the triode region if your Vout1 is less than V in Cm minus VTH. So V in Cm minus VTH. So each output will go as low as V in Cm minus VTH for the M1 and M2 transistors to be in saturation. Now the value of V in Cm, you already know, can be no less than VGS1 plus VGS3 minus VTH3. And that you know from this equation. So the minimum value of V in Cm is that. Now with this choice of V in Cm, the single-ended peak-to-peak swing at the output will be from VDD. So the maximum value could be VDD, but the minimum value could be V in Cm minus VTH. And now if you put the minimum value of V in Cm to be this, then the minimum value of your output signal will be VGS1 minus VTH1 minus VGS3 minus VTH3. So that's the overall range within which your single-ended peak-to-peak swing will be observed. Okay. Now, if you just do a large signal analysis or a DC analysis of the basic differential pair, there the objective is to determine your Vout1 minus Vout2 as a function of V in 1 minus V in 2. Now, if your RD1 equal to RD2 equal to RD, you can write Vout1 and Vout2 to be equal to VDD minus IDRD. So Vout1 minus Vout2 will be RD times ID2 minus ID1, assuming RD1 and RD2 to be equal to RD. Now, assuming the circuit is symmetric, M1 and M2 are always saturated, the current source is also saturated, and lambda to be equal to 0. In that case, the voltage Vp will be equal to V in 1 minus VGS1. V in 1 minus VGS1 will give you the voltage Vp, which will also be equal to V in 2 minus VGS2. So your V in 1 minus V in 2 is technically equal to VGS1 minus VGS2. Now, for a square law device, you already know the equation that V overdrive squared is equal to ID divided by 2 times K. Or in other words, ID is equal to half of K times VGS minus VT whole square. So that's a square law equation, that ID equal to half of K times V overdrive squared. Or V overdrive squared is equal to ID divided by half of K. So therefore, you can write VGS to be equal to square root of twice ID divided by K plus VTH. You have used this equation in your homework as well as your exams as well. So this is nothing fancy. Once again, we are using the same equations. So you can write V in 1 and V in 2 in the form of the previous equation, and V in 1 minus V in 2 will be square root of twice ID1 divided by K minus square root of twice ID2 divided by K. Now, to find ID1 minus ID2, you can square both sides of the above equation, and you can also use the condition that ID1 plus ID2 equal to ISS, and that will give you V in 1 minus V in 2 whole squared is equal to 2 divided by K times ISS minus 2 times square root of ID1 ID2. Thus, you can write half of K times V in 1 minus V in 2 whole squared minus ISS to be equal to minus 2 times square root of ID1 ID2. Now again, you can square both sides, and you can note that 4 times ID1 ID2 to be equal to ID1 plus ID2 whole square minus ID1 minus ID2 whole square. So that's just equation you have learned in your high school, right? So we can using that equation, we can write ID1 minus ID2 whole squared to be equal to minus 1/4 of K squared times V in 1 minus V in 2 whole to the power 4 plus ISS times K times V in 1 minus V in 2 whole squared. So this is a very complex equation. So we generally don't like complex equations in circuits, right? So this is something I have been telling you from the first class itself, that if you're ending up with a very complex equation, probably you're not in the right path, or probably you're doing something wrong. So in this case, we are making our life more complex than it should be. Why is that? Because remember that for this differential circuit to operate properly, what we want is that your V1, the DC points of V1 and V2 to be equal. If your DC points of V1 and V2 are not equal, then you end up with at maybe this point or that point where your Vout1 and Vout2 are also not equal. So you want your V1 minus V2 to be equal to 0, and you want your Vout1 to be equal to Vout2. So if that is the case, then if we again go back to this complex equation that we just figured out, from here, you can write down what is the value of your ID1 minus ID2. So again, you just use that complex equation, you just take the square root of it, and by taking the square root of it, you end up with this particular equation. You notice that your ID1 minus ID2 is a odd function of V1 minus V2, because you have, if you go back to the previous slide once again, that you have your V1 minus V2 in a square term here, and V1 minus V2 to the power of 4 over here. So as you take a square root, you'll still end up with a term over here as well as a term over here. So ID1 minus ID2 becomes an odd function of V1 minus V2, but it will fall to 0 if V1 is equal to V2. So if V1 is equal to V2, this term will become 0, which means your ID1 minus ID2 will be equal to 0. But as V1 minus V2 increases, your ID1 minus ID2 also increases. And you can also find out what is the value of your GM by taking a derivative of your del ID with respect to your del V in, and that will give you, again, a complex equation like this. But as I said, that if you are having a very complex equation like this, probably that's something that's not much useful to a circuit design engineer. So you have to simplify it, and you have to use it with conditions where your life becomes much more simple. How to do that? And you already know how to do that. That's basically V1 minus V2 has to be equal to 0, or in other words, your del V has to be equal to 0. And if your del V is equal to 0, then GM reduces to square root of K times ISS, right? So if you go back to the previous one, that you put del V equal to 0 for both of these cases, and then you'll see that your GM will reduce to square root of K times ISS. Remember that when we studied the GM for a transistor, we wrote this equation, that GM to be equal to square root of twice K times ID, where ID is the drain current through the transistor. Now, of course, 2 times the drain current through any of those transistors is equal to ISS, because for one of the branch, the current is, let's say, ID. For both the branches together, when the branches are in equilibrium, the total current is twice ID, and twice ID is equal to ISS. So as you see that it's the same equation, but then it could have also been represented with a much more complex form, but that's something we never use in real circuits. So if your delta V in is equal to 0, then your GM will be maximum and will be equal to something that we already know of. Again, the gain, the small signal differential voltage gain, that is Vout1 minus Vout2 divided by V1 minus V2, that reduces to this very small, very simple expression. So if you go back to the previous one, you already know your ID1 minus ID2 as a function of V1 minus V2. You already know Vout1 minus Vout2 as a function of ID1 minus ID2, because that's just RD times ID1 minus ID2. And if that is the case, your AV, the voltage gain, will become, so you probably can do this little exercise as a homework, that from this particular equation over here, just put V1 minus V2 equal to 0, and then see what would be the overall voltage gain. And in that case, your voltage gain will become square root of K times ISS times RD. Now, remember that square root of K times ISS is equal to GM. So basically your gain is equal to GMRD, which is same as your common source amplifiers that you had learned before. So there's nothing different, nothing very much different from what you have learned before. if your del V in is equal to 0. But if your del V in is not equal to 0, then life becomes much more complex and you have to deal with all these equations. All right. So if you just plot your ID1 or ID2 with respect to del V in, then it becomes a graph like this. And this directly comes from the equations that we derived in the past few slides, that if your del V in is very much larger, then all you have will be ID1, whereas ID2 will reduce to 0. On the other hand, if you have a large negative value for your del V in, then you will have only ID2, but your ID1 will reduce to 0. On the other hand, your GM will follow a plot that somewhat looks like this. That GM will be maximum at del V in to be equal to 0, but at other points, GM will be lower, which means that for you to have the maximum gain for this differential amplifier, you should have del V in to be equal to 0, and in that case, you can maximize your GM. Okay. Now, a few other consideration is that if you increase your W over L, your K will increase. If your K increases, for the same current, the del V in will decrease. Because, again, as you know from the previous equations that we learned when we learned about common source stages, that current to be equal to K over 2 times VGS minus VT whole squared. Now, if W over L increases, K increases, but if your current remains same, which is the case for a differential amplifier, then your del V in should decrease in that case. Now, if del V in decreases, it will narrow this input range across which you'll have a linear relationship between your del V in and your output quantities. Similarly, if your ISS increases, then both the input range and the output current swing will increase. So intuitively, what you can say is that the circuit will become more linear as the current through the circuit increases, or W over L through the circuit or for the transistors decrease. Okay. So this is just a representation or the explanation of the things we discussed in the previous slide. So please go over it and let me know if you have any kind of questions. What we want to discuss next is basically the small signal analysis of the basic differential pair. And for the small signal analysis of the basic differential pair, we'll always assume that all the transistors are already saturated and they are already biased in the perfect conditions. And once the DC biasing is established, we'll apply the small signal inputs V1 and V2. The differential gain Vout1 minus Vout2 divided by V1 minus V2 was found to be GM times RD from the large signal analysis already. But we'll see that even through the small signal analysis, we'll have the same amount of gain or the differential gain. Okay, now to analyze this differential circuit for small signal analysis, there could be, you can apply two different methods. The first one could be the method of superposition, where you assume that you apply one of the inputs at a time. You do not apply both the inputs at the same time, right? And then eventually you add the effects of both the inputs being applied. So first you set V2 to be equal to 0, and you want to find out the effect of V1 at points X and Y, which are the output points. Now to find Vx, you'll see that your M1 transistor will form a common source stage with a degeneration resistance. So your M1 transistor is over here. You're applying your input at the gate of the M1 transistor. Your output is at the drain of the M1 transistor. But the M2 transistor is connected at the source of your M1 transistor, and that works as a degeneration resistance. The resistance looking into the source of this M2 transistor will be equal to 1 upon GM2. So 1 upon GM2 is the resistance looking into the source of the M2 transistor. And that would be the degeneration resistance RS for this particular circuit. Now, if you neglect channel length modulation and body effect, then we already know how to analyze this common source stage with a source degeneration. And if we, for example, go back to something that we had discussed before, that common source stage with source regeneration, you have your gain to be equal to minus capital GM times capital R out, where capital GM equal to GM divided by 1 plus GM RS, R out to be equal to RD. Now, of course, your overall voltage gain will be minus GM RD divided by 1 plus GM RS. So if I again write that down, so your gain should have been minus GM1 times RD divided by 1 plus GM1 times RS. So that's the equation that we know from the cheat sheet that we discussed earlier. Now, remember your RS is equal to 1 upon GM2. So if your RS is 1 upon GM2, this becomes GM1 times RD divided by 1 plus GM1 divided by GM2. Now you divide your numerator and denominator with GM1, and you end up with RD divided by 1 upon GM2 plus 1 upon GM1, which is this equation itself. So just by putting RS to be equal to 1 upon GM2, you get this equation from that equation. Okay. So that's your gain, Vy divided by V in 1. I think yeah. So we could have also discussed this one, the Vx divided by V in 1, which is basically your common source stage with a degeneration resistance. So your common source stage with degeneration resistance is Vx divided by V in 1, that is equal to minus Rd divided by 1 over GM1 plus 1 over GM2. And that is something, again, we found out from the equation of GM minus of GMRD divided by 1 plus GMRS1. So if your RS is equal to 1 over GM2, then we end up with this particular equation. So that's your Vx over V in 1. Now for the other side, when you want to find out Vy, this is your input. So to find Vy, you can note that your M1 drives your M2 as a source follower. So M1 drives M2 as a source follower. So if you take the output at this point for this particular subcircuit, so that becomes a source follower, right? Your input is provided at the gate, output is taken at the source, and that voltage is provided at the source of the M2 transistor. So what you can do here is that your M1 is driving M2 as a source follower. You're replacing V1 and M1 by a Thevenin equivalent circuit. So you're replacing it by a Thevenin equivalent circuit with a voltage Vt and a resistance Rt, where that voltage Vt is equal to V1, because this is a source follower, so you do not get any change in the input voltage. And the resistance Rt is basically the resistance looking inside this Thevenin equivalent black box, and the Thevenin equivalent black box looking into the insides of this Thevenin equivalent black box. You see the source of the M1 transistor. So that's again 1 upon GM1. So the RT resistance that you have is 1 upon GM1. Now for M2, you have it as a common gate stage. And for that, the gain will just be positive RD divided by 1 upon GM2 plus 1 upon GM1. So as you know, that common gate stage is exactly similar to your common source stage in terms of the gain, but your polarities are just the opposite, which means that your gain is a positive quantity instead of being a negative quantity. So you can find from these two equations, you can find out what is your Vx minus Vy due to V in 1, and that will become minus of twice Rd divided by 1 over GM1 plus 1 over GM2 times V in 1. Now if GM1 and GM2 are equal and that is equal to GM, that reduces to minus GM times Rd times V in 1. Now by symmetry, you can also next apply V in 2 instead of applying V in 1. That's what we do while doing anything with superposition theorem, right? That You first apply one of the sources, assuming the other one is grounded, and then you ground the first source and apply the second source. And identically, you find out the voltages at x and y, and then eventually find out Vx minus Vy due to V in 2. And that will be equal to GMRD times V in 2. Now, adding these two results to perform superposition, you get Vx minus Vy divided by V in 1 minus V in 2 to be equal to minus Gm times Rd. So the magnitude of the gain is equal to Gm times Rd, regardless of how your inputs are applied in a half manner or a single-ended output. So for your common source, the gain was Gm times Rd. Even after having them in a differential configuration, the gain is the same, the minus Gm times Rd. Okay. So we'll stop here, and in Monday's class, we'll start discussing about analyzing the AC small signal of these differential amplifiers using another approach that is called the half circuit theorem or the half circuit approach. But using the half circuit approach, we'll still prove that the gain will be equal to this minus Gm times Rd. So as you know that till now, what we have learned is that even with this differential amplifier, your voltage gain will be similar to what you have learned with common source. With common source, the gain was minus Gm times Rd. When you have two common source transistors and use them as a in a differential amplifier, you still get minus Gm times Rd. That's your overall voltage gain. So we'll stop here and we'll start discussing about the half circuit approach on Monday's lecture. Thank you.